In the previous video, we talked a bit about the motivation behind p-adic numbers, and the idea was basically to have some kind of analog of power series, or I guess more generally you could say analysis, for number theory. So the idea, well, it started out as a rather bizarre, not very rigorous looking thing, was rather than having a sum of powers of some variable x, which might be a real number or a complex number, you could have a sum of powers of a prime, or actually any integer, but I'll say more about why we look at primes in a bit. Now, so the prime powers are increasing here, potentially infinitely far if the ANs aren't all zero beyond some point, just like we might have an infinite power series here. And similarly, we could start it at some negative bound as well. So maybe negative k to infinity, an x to the n would have an analog which would be the exact same thing, but with x replaced by p. Okay, now we saw one slightly more rigorous way of defining these things was to do an inverse limit. So rather than doing these base p expansions, you take something mod p, and then you take something congruent to that, but now mod p squared. So whatever number you pick mod p squared has to reduce mod p to what you picked in z mod p. And then you take something in z mod p cubed that reduces to what you picked mod p squared, and so on. Okay, and now the integers mod p can be thought of as the constant term. Then if you have something that's congruent to a0 mod p, in the next ring it's something like a0 plus some multiple of p. And then in the next set you have what you had in the previous step, but plus some multiple of p squared, and so on. And then in the limit, well, the inverse limit, you get essentially this expansion that we had before. So that's what led us to define the p-adic integers as the inverse limit of z mod p to the n z. Okay, and then the p-adic numbers, which were, you could either think of them as the field of fractions of zp, or what you get from taking negative powers of p as well. But it's important that the powers of p are always in increasing order. You can't have anything like 1 over p plus 1 over p squared plus 1 over p cubed, and so on. Even though that makes sense in the usual number systems we use, it won't make sense in QP. So you have to really do a Laurent series in P, meaning you start at some negative bound, but you only increase from there. Okay, now this is still quite abstract, and it isn't clear how it's actually useful. And actually, when Hensel first described these p-adic numbers, there were some pretty big issues with making it all rigorous and understanding how to use these weird objects to answer questions in more traditional number theory contexts. So it actually took mathematicians a few decades to really make it all rigorous. Now, one more way of thinking about these p-adic numbers is as completions, and this is what will allow us to generalize these kinds of number systems when we get to that later. So the idea behind a completion is, so for example, R is a completion of Q. With respect to, well, the usual absolute value. By the way, I may end up writing it as the usual absolute value, but with an infinity subscript. So in some sense, this is like QP, but where P is thought of not really as a usual prime, but as infinity. Okay? So this is sometimes called an infinite prime. Okay, so it's kind of a strange terminology, but over time, as we get further into the theory, we'll see how, in a lot of ways, this really does act a lot like these other completions, the more exotic ones that give the QPs. And, well, for one thing, if you let P be infinity, then I don't have to keep saying QP and R. I could just say QP, and that includes the completion that we're used to. But anyway, so this is probably the first kind of completion that one sees when one is learning about metric spaces and Cauchy sequences and all those fancy terms. The idea is really just, okay, the rational numbers have some gaps. So, okay, it's not really possible to draw them, but here's the real line. And, okay, maybe there's 0, there's 1, there's -1. Okay, if I were to plot all the rational numbers, if I could somehow do that, I would get a bunch of points all over the place. Of course, they're dense in the real numbers, so there aren't actually any real gaps, in the sense that there are no gaps of non-zero width, but there are still lots of points that you miss. So for example, square root of 2 is not in here, so in some sense the rationals skip over that. But a completion means you just take all the possible limiting values of sequences in Q. So, in more rigorous language, you'd say something like, it's the set of all equivalence classes of Cauchy sequences, and then, okay, that gives a huge set, and it's pretty annoying to actually go through all the details, but basically a Cauchy sequence in this case is one that tends to a limit where the numbers and the sequence are getting closer and closer together, except that limit may not actually be in Q, even if the original numbers are in Q. So an example of that for root 2 would be, well, you could just take all the approximations to root 2. Okay, now this sequence approaches root 2, and the terms are getting closer and closer together, but root 2 is not in Q. So that's what it means to say that Q is not complete. It means that there are somehow these gaps. So when we fill in the gaps, we get the real numbers. So now when I say Cauchy sequence, that means the terms are getting closer and closer together. So if I have two terms am and an, that's going to 0 as m and n get big. Okay, but there's this implicit assumption, which is that I'm using the ordinary absolute value here. Okay, so this is why R is the completion of Q with the ordinary absolute value. But there are other absolute values. So those are what lead to the QPs. So first, maybe I should actually give some definitions for what I mean by absolute value. So in number theory, it has a very precise meaning. So it usually is written like this, although there may be some subscript down here to specify which absolute value we're talking about, but let's not worry about that for now. So for one thing, it should always be non-negative, and it's 0 if and only if x is 0. Also, we want it to be multiplicative. Okay. And the last axiom is that we want it to satisfy the triangle inequality. Okay, so these outputs of the absolute value are real numbers. They may not be rational, although with the examples we look at, they will be rational numbers. And you can define these absolute values on fields other than Q, but we won't get to that just yet. Okay, so certainly the usual absolute value does satisfy these things, but there's one other kind of absolute value that leads to these QPs. So to motivate this, remember we thought of these things as informally being power series, or maybe Laurent series in P. I may occasionally write power series, even when I'm talking about p-adic numbers rather than integers, just because that's kind of my implicit assumption, I guess. But the same thing works for Laurent series as well. So, okay, I'll write in the first few. There. Okay, so the idea is that, well, for this to converge in some sense, these terms have to be getting smaller and smaller. Okay, so the idea is we want an absolute value where high powers of p are considered small. Just like how with power series in x, large powers of x are in some sense small. At least when you're talking about convergence, when you actually plug in a small value of x. Okay, so we want, well, what we end up wanting is the powers of p to go to 0 in absolute value as k goes to infinity. Okay, again, this is weird, but well, it takes some getting used to, and I hope with some examples we'll see how these things are useful, and over time I hope you come to appreciate them and not think of them as being extremely weird, even though they are in a lot of ways. Okay, so we want the absolute value of p to the k to go to 0 as the exponent goes to infinity, but we also have this multiplicativity condition. So basically, as long as we have an absolute value where the absolute value of p is less than 1, we'll be okay. Okay, so we want numbers divisible by large powers of p to be small. So that's what leads to something called the p-adic valuation. So the p-adic valuation is written VP. Okay, and it's a complicated word for something very simple. It's just the highest power of p that divides that integer. Okay, but there's no reason that n has to be an integer. We could take the p-adic valuation of a rational number. And you do the same thing, except you might get a negative power if you have p's in the denominator. So for example, the 5-adic valuation of 125 is 3, whereas the 7-adic valuation of 2 over 49 would be negative 2. So you take the largest power of 7 going into 2 over 49, which is a weird way of phrasing it, but it's negative 2 because you take the largest power dividing the denominator, and that's going to give you a negative 2. Okay, so this gives us a way of counting the powers of p that go into any rational number. Okay, things are a bit weird with 0, so we usually say that VP of 0 is infinity, which makes sense because, well, any power of p is a factor of 0, so we can go as high as we want. So if we give it a value, really infinity is the only value that makes sense. Now, with this p-adic valuation, we can define our absolute value. So really, once you define this absolute value on p, you pretty much define it everywhere. And we just want it to be less than 1. But it turns out to be most convenient to say that its absolute value is 1 over p. Okay, and, well, I'm going to write a subscript p, so there are a lot of p's floating around. But for the p-adic valuation, the absolute value of p is 1 over p. So in general, the absolute value of p to the k is 1 over p to the k. And for a rational number r, the p-adic absolute value is the reciprocal of p to the power of the valuation. Okay, so again, complicated notation for something simple. So for example, the 5-adic absolute value of 125 would be 1 over 125, and the 7-adic absolute value of 2 over 49 would be 49. Okay, so you just take the highest power of p that goes into it, but you take the reciprocal, and that's your absolute value. Okay, so with this absolute value, this will make these powers of p go to 0, and remember up here we had these a's being integers, and, well, if we're thinking about them in terms of base p expansions, they shouldn't be divisible by p. So if we have this base p thing again, okay, maybe some negative powers again, then the p-adic absolute value of this, well, we're assuming p doesn't go into an. So it's p to the minus vp of this whole mess. But the an doesn't affect it at all. So it's just p to the minus n. And that matches with the multiplicativity condition on the absolute value. So if we use multiplicativity, it turns into this. Okay, subscript p's. And, well, the p-adic valuation of an is 1, because p doesn't go into it at all. So, sure enough, we do get 1 times p to the minus n. Okay, now, just to prove that this really makes sense so that I'm not trying to do any kind of trickery, I'll show that this really satisfies the axioms we want. So first of all, we want to show that the p-adic valuation of any rational number is non-negative. Okay, well that's silly because p to any power is non-negative. Now, there was that one detail of what happens when x is 0, and remember I said that vp of 0 was infinity, and that would make it so that the absolute value, okay, bad notation incoming, would be p to the minus infinity. Okay, so the only real way to make sense of this would be to say that it's 0. And that does check out with this condition that it's 0 if and only if x equals 0. Okay, so those two are good. Multiplicativity, well, that's pretty straightforward as well. Because, well, the largest power of p dividing xy is the largest power of p dividing x plus the largest power of p dividing y, and then that corresponds to addition of the valuations, and that's multiplication of the absolute values. Okay, so there isn't a whole lot to that one. This reciprocal business doesn't affect that multiplicativity, but we do need it for, well, for this condition, and we need the reciprocal for the triangle inequality. So for the triangle inequality, we want to show that the absolute value of x plus y is at most the absolute value of x plus the absolute value of y. I'll put a check mark here. Okay. Now, in fact, so this is called the triangle inequality, but the p-adic absolute value satisfies something stronger, which appropriately is called the strong triangle inequality. It satisfies this condition. Okay, so rather than taking the sum as the upper bound, I can just take the larger of the two absolute values. Okay, now again, this is just going to turn into a pretty basic number theory fact. So let's say p to the m divides x. Okay, this notation means fully divides, so that's the highest power of p dividing x, so the valuation of x is m. And let's say p to the n fully divides y. Okay, so then the right side is just, we're comparing p to the minus m and p to the minus n, and we'll take the max of that. Okay, then on the left, we're looking at how many times p goes into x plus y. Well, if p to the m goes into x and p to the n goes into y, then the smaller of those powers goes into the sum evenly. So we could say that if we take the minimum of m and n, that divides x plus y. Okay, we don't know the exact power of p dividing it. We could even have x plus y equals 0, in which case the power is infinite, but that isn't too important here. Okay, so the valuation of x plus y is at least the smaller of m and n. Okay, now when we take reciprocals, we're going to get exactly the right-hand side. So this says that the p-adic absolute value of x plus y is at most p to the minus minimum of m and n. Okay, so if x plus y is divisible by a larger power of p, the absolute value will be smaller than that, but that is an upper bound. And this is the same as taking p to the minus m and p to the minus n and taking the larger of those two. Okay, so nothing really scary there. It's really just saying if some power of p divides x and some power of p divides y, then the smaller one divides the sum. That's really all there is to it. Okay, so this is a valid absolute value. And now we can take the completion with respect to this. So we can look at what happens when we have a sequence of rational numbers where the differences between these go to 0 with this p-adic absolute value. Okay, so what does that mean? Well, maybe it's easiest to think about what it means for integers. So with integers, it means that the differences are divisible by higher and higher powers of p. So now if we go back to this inverse limit idea, so if the differences of these x's are divisible by larger and larger powers of p, that means that, for example, the differences are eventually all divisible by p. Okay, so that means that mod p, we eventually get a constant. Okay, so for example, you could have something like 1, 2, 3, 8, 13, 38, 163. Okay, so if we take these mod 5, well, the 1, 2, 3, those, the differences of those are 1 in the 5-adic absolute value because the differences aren't divisible by 5 at all. But 3 and 8 differ by a fifth. 8 and 13 differ by a fifth. 13 and 38 differ by 1/25th. 38 and 163 differ by 1/125th, and so on. Okay, so if we reduce these mod 5, we eventually get 3, 3, 3, 3, 3, 3, 3. Okay, so okay, and then if we do mod 25, well, it may take longer to stabilize, but it will stabilize. And then we just keep going down that way. So we really do get essentially the same thing as the inverse limit, just defined in a slightly different way. So these x's are integers, and that gives the p-adic integers when we do this sort of completion. But if we do this with rational numbers where we allow some kinds of denominators divisible by p, the completion will give us qp. So an example of that, well, maybe it's easiest to see an example where I actually write it out with this sort of base p notation. Okay, so if I look at the differences of these two, well, they differ by 3, but in absolute value, with the 5-adic absolute value, that's a difference of 1. Here the difference is 1. Okay, here the difference is 1/5, because the 7 and the 12 differ by 5. Okay, and we can keep going like this. And we can have denominators that aren't divisible by 5 as well if we want. But when we do that, we can write them actually as p-adic integers. Okay, so I guess that's a fact that I haven't proved yet. So we definitely know that we can fit Q inside QP because, well, for one thing, if you think of it in terms of this completion idea, Q has to be in there. But even in terms of the base P idea, so if we take a rational number with A and B integers, we can write the numerator and denominator in base P in ascending order of powers. And then you just expand it with this power series trick and you get something in QP. So there might be some factors of P down here if some of the B's are 0, but after a certain point you'll get only non-negative powers of P, and the powers of P will be increasing, and if you reduce those mod P, then P squared, P cubed, and so on, they will eventually stabilize. Just like how with power series, if you have something like 1 minus x plus x cubed over 1 minus x to the 10th, you treat this as a geometric series where, well, you write it like this, and this x plus x to the 10th is your common ratio, and when you expand it out, you're taking powers of that, and since x goes into it, the powers of x are increasing, so there will only be a finite number of terms that contribute to any of the coefficients. Okay, this wouldn't work if we tried doing something like that. Okay, we could still write it as a Laurent series, but we couldn't do it by expanding powers of 1 plus x to the 10th because we get an infinite number of terms with constants, and that's bad for convergence. So as long as you have something divisible by x in the common ratio, or in the case of p-adic numbers, something divisible by p, you're okay. Alright, so Q goes into QP, but in fact it turns out that if I take a rational number and its p-adic absolute value is at most 1, meaning that no p's go into the denominator, then you could think of this as actually being a p-adic integer. Okay, so that's really a consequence of this power series idea again. So as long as b0 is not 0, you can expand this as you would an ordinary geometric series, and you won't get any p's in the denominator, so you'll get a power series in P rather than a Laurent series in P. Okay, so we've shown that R is the completion of Q with respect to the usual absolute value, which I may write with a subscript infinity to differentiate it from the QP's, and then the QP is the completion with respect to the p-adic absolute value. So when you have numbers getting closer and closer together with higher and higher powers of p, they stabilize mod any prime power. So in the limit you get something in QP. So next time we will discuss Ostrovsky's theorem, and we'll prove it, which says that R and QP are the only completions of Q with respect to an absolute value satisfying those axioms. So non-negativity, it's 0 if and only if x is 0. It's multiplicative, and it satisfies the triangle inequality. With those axioms, R and QP are the only things you can get. So we will prove that next time.